So today's class is Computer Organization, Module 3, Lecture 2. Now last day we learned about the different types of memory, and I told about the cache memory. What is the function of the cache memory? You already know that cache memory is a special type of memory. This is a high speed memory which is in between the main memory and the CPU. That means it is used to bridge the speed difference between the CPU and the main memory. Okay, and here it is used in the computer organization. Cache memory is generally used to speed up the performance of the system. This is the objective of using the cache memory. Now here it is written that it is a high speed memory device in between CPU and main memory, and it depends on the phenomena of locality of reference. What is locality of reference? I will tell later. And it will increase the overall performance of the system. This is the cache memory. Okay, and cache memory is one of the important part in the computer organization and in the memory organization of a system. Now I have already told that there are two types of random access memory. Remember that cache is also random access memory. There are two types of access memory. One is random access, another is sequential access. I have already told you that sequential access is a slow device, random access is a high speed memory. So cache memory is also a random access memory, and it is a static memory. RAM are two types. One is the static and dynamic. Static RAM is made up with the traditional flip-flop. Dynamic RAM is made up with the capacitor. As the capacitor has to be charged, dynamic memory is slow, but cost is also low in case of the dynamic memory. So dynamic memory is used to make the main memory, and cache memory is made up with the static memory. So this is the cache memory. Now see here, this is how the cache memory actually works. Okay, here it is given. See in the figure, here in the left hand side there is a CPU, and right hand side there is a main memory. In between the main memory and CPU there is a cache memory. Now what happens? I have already told that when CPU wants to execute any program, it stores the program into the main memory. Now when cache memory comes into play, instead of the main memory, CPU will take the data from the cache memory. That means suppose CPU want to execute a set of the program is stored first obviously into the main memory. Then the program which is required to be executed will be transferred from the main memory to the cache memory, and CPU will take the data or instruction from the cache memory and then it will execute. Okay, so at first when any address is generated, what is the requirement of address? Requirement of address is to find out where the instruction and the data is stored, because this is a stored program concept. So when the address is generated, CPU will first search the cache memory to find out whether the instruction is stored into the cache memory or not. If the instruction is stored into the cache memory, what will happen? It will execute the data from the cache memory, or it will execute the instruction from the cache memory. If it is not stored into the cache memory, it will go to the main memory and it will take the data from the main memory, put the data into the cache memory, then it will execute. Now first CPU search in the cache memory. If the data is present into the cache memory, then that is called the cache hit. That means the instruction or the data is present into the cache memory. That means this is called the cache hit. Okay, and it will execute. If it is not present into the cache memory, okay, if the data or instruction is not present in the cache memory, that phenomena is called the cache miss, and CPU will go to the main memory. Okay, then it will transfer the data. Here it is written, transfer the data into the cache and execute. That means from this it will transfer the data into the cache memory, then CPU will execute. So what is the process of execution? CPU first search into cache memory. If it finds the data, that is a cache hit, it's fine, it will execute the data. If it does not find the data, that means that is called cache miss. It will go to the main memory, bring the data or instruction from the main memory to the cache memory, then it will execute. So in this way, cache memory with the help of the CPU and main memory works. Okay. Now, how to find out whether that data is present into the cache memory or not? For this, there is a special field that is called the tag field. CPU will check not the total address. Always remember that whether the data is present into the cache memory or not depends upon the address. Address is generated by the CPU. CPU will check the address, that whether the data of this address is present here or not. Clear? That means it will not check the, that means it will check the address, but it will not check the whole address. It will check the part of the address. That means it will be the most significant bit position. That means the upper position bits. Okay, that means the depth mode bits it will check to find out whether the data is present or not, and that is called a tag field. When I will give you the example, it will be more clearer. That is called the tag field. That means CPU will check the tag field whether the data is present in the cache memory or not. If it is present, I have already told that is cache hit. If it is not present, that will be cache miss. So how to find out this? Using checking the tag field. Clear? If the tag field is present, then data is present. If it is not present in the tag field, that means data is not present here. Clear? Now, see here, I have already told that there is a phenomena called locality of reference, and cache memory mainly depends on the principle of locality of reference. Now, what is the principle? Here it is written, the principle states that memory reference tend to cluster. Over a long period of time, the clusters in use change, but over a short period of time, the processor is primarily working with the fixed clusters of memory references. So what is the meaning of that? Here, I have written a small piece of code. See here the code. The code is, this is in the pseudo language. There is not any particular language. A is equal to 1, B is equal to 20. This is the initialization of the variables A and B. And then for I is equal to 1 to 1000, B is equal to B plus 1, end. Clear? Now, if processor want to execute this piece of the code, what will happen? See here, this A, it will execute one time. B is equal to 20, A is equal to A1, it will execute one time. B is equal to 20, it will execute one time. But this block, for I is equal to 1 to 1000, B is equal to B plus 1, end. Starting from for up to end, this piece of the block will be executed 1000 times. What? See here, this is 1000. It will be executed 1000 times. So what is the meaning of that? Meaning of that is, if this is the total part of the program, this part of, if this is a total program, this part of the program starting from this line to this line, for to end, this program will cluster, or processor will cluster only on this block. So it is written that memory references tend to cluster. Cluster means it will execute the same block of code again and again. So what will happen if processor puts this block of code into the cache memory? Obviously in the program, remember, this block of the code will take the maximum time because it will go for the 1000. This operation will go for the 1000 times, so it will take maximum time. So if it takes maximum time, and if I put this block of the code into a high speed memory like the cache memory, and then if it takes minimum time to execute, obviously system performance will be increased. Okay, suppose this in the main memory, each instruction execute 10 seconds. Memory reference time is 10 seconds. So it will 1000 into 10, that means 10 to the power 4. Total time required would be 10 to the power 4 nanosecond if it is 10 nanosecond. But if I put in the cache memory, which is high speed memory, suppose here the memory access time is 1 nanosecond, then it will be only 10 to the power 3 nanosecond, because 1000 means 10 to the power 3 into 1, that means 10 to the power 3 nanosecond. But if it is put in the main memory, it will be 10 to the power 3 into 10, that means 10 to the power 4 nanosecond. Obviously main memory will take the more time. So if I put a cache memory and if I put this block of the code in the cache memory, which will execute again and again, the total time required will be low and the system performance will be up. So this is called the locality of reference. That means this locality will execute again and again. If I put this parts of the code into the high speed memory, obviously the system performance will be increased. Now see the numerical of the cache access time. Okay, now suppose probability of hit is h. What is the meaning of that? Meaning of that is that the data is present into the cache memory. Probability of the phenomena that the data is present into the cache memory is h. Obviously h will be vary from 0 to 1, because you know that probability value, maximum value is 1, minimum value is 0. So probability of miss, what will be the probability of miss? 1 minus h. Clear? Then what will be the average access time? So average access time of the memory will be h is equal to, here it is written here, h into tc by plus 1 minus h into tc plus tm, where tc is the cache memory access time, tm is the main memory access time. Now though, how to find out this calculation? Now see here, what is the probability of hit? Probability of hit is h. That means there is a chance that out of the 10, h times the data will be present into the main memory, cache memory. So if this is the probability of hit and tc is the cache memory access time, that means then what will be the access time if it is present in the cache memory? H into tc. Clear? Then if it is not present in the cache memory, that means the probability of miss. Probability of miss is 1 minus h. If it is 1 minus h, what I told you, that processor has to go to the main memory. Processor has to bring the data from the main memory to the cache memory, then it has to execute. That means there are two memory access. One is the main memory, so that is the tm, and another is the cache memory again, because for execution it has to again fetch the cache memory. So tc plus tm, this is the total memory access time if there is a miss. So 1 minus h is the probability of miss. So 1 minus h into tc plus tm, this is if it is miss, then this will be the time taken. So what is the average time? You know, average time will be this h into tc plus 1 minus h into tc plus tm. Clear? So this is the total time. So what is the efficiency of the system? Efficiency of the system will be 1 by t, because always remember efficiency varies with the time to access the memory. If the memory access time is more, efficiency will be low, and if the memory access time is low, efficiency will be high. Because as the memory access time is very high, obviously time to execute one program will be high, so efficiency will be low. Similarly, if the efficiency total average access time is low, program to execute one program will be low, so efficiency will be high. So this is the calculation of the efficiency. Okay, now see one problem. This is the first problem. The problem is, in a system the probability of cache hit is 0.6. What is the meaning of that? That means if there are 10 instructions, out of the 10 instructions, 6 instructions will be present into the cache memory. Clear? That means 60% instruction will be present into the cache memory. Now the main memory access time is 4 nanoseconds and cache memory access time is 8 nanoseconds. See here. Oh, there is a problem here. I am written. It should be main memory access time should be 8 nanoseconds, because main memory access time always will be larger than the cache memory. Okay, just you make it that I have done some wrong here. It should be main memory access time should be 8 nanosecond and cache memory access time should be 4 nanoseconds. It should be low. So main memory access time is 8 nanoseconds. Clear? Then cache memory access time is 4 nanoseconds. Now What is the average access time? You know that T is equal to H into TC plus 1 minus H into TC plus TM. So 0.6 is the cache hit into 4. 4 is the cache memory access time plus 1 minus 0.6. This is the probability of miss plus this is the cache memory access time. This is the main memory access time. So 7.2 nanosecond is the memory average memory access time. If you want to find out the efficiency, you have to do 1 by 7.2 is the efficiency of the system. Clear? So this is the one numerical. Now see here, see it carefully. This is very important for our cache memory organization. See here, this is the main memory. Clear? Last day I told about what is the specification of the RAM and how the data and address is specified in a RAM. Now here, see here, this is 0000, 0001, 0010. These are the physical address of the RAM. What is the number of the physical address here? Number of the physical address is 16. So what is the address bit? Address bit here is the 4. So 2 to the power 4 is equal to 16. So these are the physical address of this particular physical location. They are called the words. Again, I am telling you these are the address of the address locations. They are called the words. That means 0000, 0001, 0010. These are all the address of the words. So what are the words here? Here the words are suppose 12, 23, 14, AC, F2, 21. These all are the different data and each data is called a word. So what are the address of the word? These are the all the address of the physical address of the word. Here, what is the specification of this RAM? Here, this is a hexadecimal code. So what is the number of the bits required? Number of the bits required is 8 because one digit 4 bits, another digit 4 bits. So there are 2 digits, so 8 bits. So 8 into 16. The specification of the RAM is 8 into 16. So this is the RAM. Now, this is the physical address of the RAM. Now remember, in the computer organization, we can divide this physical address into a number of the logical address. Clear? What is logical address? See here, logical address means here the total RAM is divided into block and word. Clear? Here the total RAM is divided into blocks and words. So what are the blocks? Blocks is a set of words. What is the definition of the block? Block is a set of words. Now see here, suppose here right hand side I have written the block number. So this is a block. Block is a set of words. This block contains 2 words, this and this. So I have written it within the bracket. Similarly, this is a block. It contains this word and this word. Clear? Similarly, this is a block. It contains this word and this word. This contains this word and this word. This contains this word and this word. That means in the right hand side, you can see that the memory is divided into blocks and each block contains 2 words. Okay, I repeat, the memory is divided into blocks and each block contains 2 words. Similarly, see in the left hand side. Left hand side also the memory is divided into blocks, but here there are 4 blocks. Remember, this division is only a logical division. This is not a physical division. Clear? So here there are also, what is the total number of blocks? 4 blocks, and each block contains 4 words. 1, 2, 3, 4. This is for block 0. Then 1, 2, 3, 4. This is for block 1. Then 1, 2, 3, 4. This is for block 2. And 1, 2, 3, 4. This is for block 3. That means there are 4 blocks. Each contains 4 words. So 4 into 4, 16. So we'll get 16. In the right hand side, there are 8 blocks. Each contains 2 words. 8 into 2, 16. Again, we got the 16 address. So this is a logical division. Now that means each physical address can be divided into two addresses. One is called a block address, another is called a ward address. Clear? Now we will try to find out, if one physical address is given, how to find out the block address and how to find out the ward address of that particular physical address. Clear? Again, I am telling, each physical address is divided into a number of the blocks. Each block contains a number of wards, and each physical memory is divided into certain blocks, where block is a logical division, not a physical division, and each block contains a number of the wards. Now we have to find out how to represent one physical address into block address and one address. Clear? Now see here. See in the bottom, there is an example. Suppose you are given a physical address 1001. Clear? You asked, you have to find out what is the block address and the ward address of the particular physical address. What is the physical address? Physical address is 1001. Now see here, for right hand side, what is the total number of the wards in a block? There are 2 wards in a block. See carefully, there are 2 wards in a block. That means W0, W1. Here also W0, W1, W0, W1, 2 wards. So what is the number of the address bit required for addressing the 2 address? That is 1 bit is required, because 0, 1 address, this is 0 address, this is 1 address, 0 address, 1 address, 0, 1. So 1 bit is required to address a word in a block. Again, I am telling, a block contains 2 words. So what is the number of the bits required to address each word in a block? Each word in a block, it will be 1 bit, because 1 bit represent either 0 or 1. 0 means 1 address, 1 is the another address. This is another address, 0, this is 1. Again, this is 0, this is 1. This is 0, this is 1. So 1 bit is required for the word address, and the remaining bits are for the block address. Why? What is the total number of block here? Total number of the block is 8. Number of the bits required to address the block will be 3. So 3 means 2 to the power 3 is equal to 8. So in a physical address, the upper portion, that means the most significant bits, will be required for addressing the block, and the least significant bits will be required for addressing the word. Now you know what is the total number of word. Here in this case, total number of word address, suppose in this example 1001. So I have already told 1 bit is required for addressing the word and 3 bits are required for addressing the block. So what is the block address? I have told you the upper bits, upper 3 bits here in this case, because 3 bits is required for the block. So 1, 2, 3. So 100, this is the block address, and 1 is the word address. What is the meaning of that? What is 100? 100 means 4. Clear? So see here, if I come here, so see here, 100, this is the block 4. See this 1001. So this is the block 4. So this is the block 4. In the block 4, what is the word number? Word number, this is 0, this is 1. So see here, 1001. 1001 is the word number. Again, I am telling, here 1001, 1 bits is for the word, and remaining 3 bits for the block. So 3 bits means 100, and 1 bit, last 1 bit means this is 1. So block is 4, word is 1. We'll directly go to the block 4, and 1, block 4 means this. It contains 2 words. Within the word, which word I required? I require word address 1. So word address 1 is this, because this is 0, this is 1. So 1001. So what is the data? E3. So if this address is given, we'll read the data as a E3. And directly you can go from, if this is a physical address, actually you will go from this to this. So this is the block 4, word 1. Similarly, the same thing we can do in a numerical way. What is the numerical way? What is the 1001? What is the decimal of 1001? Decimal of 1001 is 9. Now each block contains 2 words. So I will divide 9 by 2. The quotient is the 4. Okay, 4 into 2 is equal to 8. So quotient is the 4 and remainder is the 1. 9 mod 2 is the remainder is the 1. So this is the fourth block and number 1 word. The same result we have got in the binary system also. See here, this is the fourth block, 100 is 4 and what address is 1. This one is equal to this and this 4 is equal to 100. Okay, so in the two way we can find out what is the block address and what is the word address. One using the binary number and another using the numerical system. See that another example in the left hand side. In the left hand side, the logical division, but here each block contains 4 words. Previously it was right hand side, it was the 2 words, left hand side it was the 4 words. 4 words means what is the number of the bits required to address each word? 2 bits, because 4 words means 00, 01, 10, 11. What is the number of the bits required? 2 bits to address the word. What is the total number of bits here? 4. So 2 bits are required for addressing the word. What is the remaining bits? 4 minus 2, that means 2 bits. So 2 bits are required for the block address. Clear? That means here in the left hand side, for word address 2 bits are required because there are 4 words in a block, and for block address 2 bits are required because what is the total number of block here now? 1, 2, 3, 4. So 2 bits here. So 2 plus 2, it will be 4. Now see the same example. Here the physical address is 1001. Clear? So 2 bits required for the block address. So now the block address is 10. And what is the word address? Word address is the last 2 bits 01. Now what is 10? 10 means what is the decimal of 10? Decimal of 10 is 2. That means it should be B2. See here, I directly go to the B2. Okay, and word address is 1. That means in the block B2, word is 1. So this is the B2. B2 starts from here to here. So I first go to the B2 and I go to the address 1. So this is a 0 address. This is a 1 address. So E3. So this is say here the same 1001. Clear? That means block. Again, I repeat that block address is 2. Word address is 1. That means 0, 1, 2. I'll first go to the block address 2, and in the 2 in the word I will search the word number 1. This is the word number 0. This is the word number 1. So I require this word. See, the physical address is 1001. So this is 1001. So numerically we can calculate in the same way. Here 1001 means 9. In this case this is 4 because each block contains 4 words. So we have to divide it by the 4. Previous case it was 2. So 9 by 4, quotient is 2. That means 9 by 2, 4 into 2 is equal to 8. So quotient is 2, and 9 mod 4 divisor 9 mod 4 is equal to remainder is 1. So block 2 word 1. So here also the same result, block 2 word 1. So we can do the calculation using the binary system and using the decimal numerical method. Okay, so this is the address representation. This representation, remember, is very much important to understand the cache memory system. Clear? Now see the next 2 problem I will show. First problem, in a system number of the address bit is 7. Clear? The address is divided into blocks and each block contains 4 words. What is the block address and word address of the physical address 30? This is the question. Okay, that means the system has a 2 to the power 7 bits and the physical address is 30. So first we have to do first solution 1. That means this solution using the binary system. Clear? What is the solution 1? Solution 1 means first the binary of 30. What is the binary of 30? You can calculate. That is 0, 0, 1, 1, 1, 1, 0. Clear? Now the address is divided into blocks and each block contains 4 words. So if each block contains 4 words, what is the number of the bits required to address the word? 2 bits. So from the left hand side we will take 2 bits. So number of the bits in the word is 2 bits, 0, 1. So this is the word address is 10 left hand side. I'll take these 2 bits, so 1 0. So word address is 1 0, that is 2. Clear? And what is the block address? Remaining address will be the block address. Okay, so what is the remaining address? 00111, because 00111, because this 2 is required for the word, and the remaining one 11101, this is for the block address. So what is the block address? 00111. What is the decimal of this 00111? 7. That means if the physical address is 30 for this system, the block address, corresponding block address will be 7. That means you have to go to the block 7, and the word address will be 2. Clear? So this is the solution 2. Solution 2 is the same using the numerical. So as each block contains 4, we have to find out the word address as 30 mod 4. Previous slide I will show you that to find out word address you have to do 30 mod 4. What is the result? 2. And to find out the block address, 30 by 4, that is the quotient is 7. See here, so 7 is the block address, this is the 7, and this is the 2 is the word address. Clear? Again, I'll show another problem. This is the last problem. In a system, number of the address bits is 5. The address is divided into blocks, and each block contains 4 words. The same. What is the physical address of a data if block address and word address of the data is 5 and 3 respectively? Here, that's the reverse of the previous question. Here, we have to find out the physical address given the block address and the word address. Clear? That's the reverse. Previous case, from the physical address, we have to find out the block address and word address. Here the reverse, from the block address and the word address we have to find out the physical address. Now see the solution. Solution first, binary of 5. Why 5? Because what block address is 5. What is the binary of 5? 101. This is the binary of 5. Binary of 3, 1 1. Clear? So what is the physical address? This is the upper bits. So 101, I put here 101. Then I put the word address. This is the block address. First I put the block address 101. Then I put the word address 11. Check what is the number of bits? 1, 2, 3, 4, 5. In the question C, the number of bits is given 5. So it is okay. So if I make a decimal of this number, that is 23. So the system whose that particular address, whose block address and word address is 5 and 3 respectively, will have a physical address 23 into the main memory or RAM. This is the solution 1. Now this is the another solution. The same solution. Each block contains how many words? 4 words. And what is the block number? 5. So what is the total number of words up to 5th block? That is 5 into 4. Okay, plus we will go inside the block up to 3 address. So 5 into 4 plus 3. So this is the 23. See, we'll get the same answer using this. Clear? So this is the concept of dividing one physical address into block address and word address. This is required for mapping the cache memory, which I will discuss in the next day. Okay, so you must go through this lecture and make the conception very clear to how to divide the number into address into the physical address and logical address. So this is all for today.